We've just discussed that the average is a new type of random variable. In particular, it's this specific linear combination. Now, if we assume that our random variables are all independent of each other, then earlier we showed that the expectation of the average matches the expectation of each individual random variable, and the variance of the average is reduced when compared to each individual random variable. And this is the big advantage of the average. Now, we want to go a little bit further because we want to try to use averages in our probability models. In order to do that, we need to know about the distribution that an average follows. So, what shape does the X bar random variable have? Now, very naturally, you would assume that this depends on the shape of each individual random variable. So we are going to make an assumption, and we're going to introduce a new term here. We're going to assume that each xi is not only independent, but we're also going to assume that it's identically distributed. So each xi is independent of all the others, but they all have exactly the same distribution and therefore the same expected value and variance like we assumed above. So in that sense, we're going to introduce this acronym IID. So whenever we see this IID, it's meant to suggest that each random variable we consider is always independent of all the others and is identically in the sense of distribution. So we are going to talk about a very special case. We are going to assume that each xi is a normal distribution. And we are going to assume it's some normal variable with mu and sigma squared. And we are going to assume that they are IID with this particular distribution. Now I'm going to give you some properties in this particular case, and I'm not going to prove them just because some of it is tedious and some of it requires more calculus than we have at our level. But the first property says, look, if we've got a single random variable that's normally distributed with a mu and sigma squared, and if we define a linear function of it, y is ax plus b, then it will turn out that y is also a normal random variable, but its properties change. Now its normal, its expected value is shifted in exactly the same way as the function, and just like we assumed before, the variance only cares about the weighting in the front. So the first property says that if you shift and stretch a bump, it's still a bump. If we now have two separate normal variables, and so now if we have x1 being some normal variable that has its own mean and variance, and if x2 is some normal variable with its own mean and variance. So we are now stepping away from the whole IID business, but we are trying to come up with some basic properties related to these. It will turn out that if you have two normal distributions and you want to add them, you will end up with another normal distribution. Its mean will simply be the sum of those means, and its variance will simply be the sum of the other variance. So in plain, informal words, the sum of two bumps is still a bump, right? So if you put them together, you can now talk about lots of different normal random variables. So if we've got xi, and they are all different and they all have their own means and they all have their own variances. And if we assume that they are independent, that's the main assumption that we're going to make here. They don't have to be identically distributed. They just have to be independent. It will turn out that if we take this usual generalized combination of them, this combination will still be normal. Now, it's a little bit messy to write here. We'll have the sum of this A mu I plus a B as the nu. So basically, you're just adding up all the individual means and plus shifting it by this B. And you'll also have the sum of all of these AI squared sigma I squared. Now, you don't have to memorize that. That's something that's somewhat intuitive and you can look up. But the key result, the one that we are really interested in most, is if you now take the average and you define the average as the sum of all of these normal variables for xi being iid and xi being normally distributed like this. So if we were to take this average of all these identically distributed results, what we will then show is that the average itself is a normal variable. It has the same expected value as the individuals, and we proved that earlier, but it's got a reduced variability. We also proved that earlier. So the average of normal random variables is still normal. But the key idea is that it has reduced variability. And that's really important because the reduction of variability means that we are more certain when we talk about probabilities. The spread here is less than it would be in a normal situation. So the standard deviation would be sigma over root n. And that becomes very useful. And as an example, I believe this was related to something that was done in class before, but it's the sugar packing machine example. So we are told that a single sugar packing machine doesn't exactly spit out 1 kilogram. It spits out masses according to this normal distribution. So suppose that this is the case. If we are going to talk about underfilled, a bag is underfilled, a 1 kilogram bag is underfilled when you don't have 1 kilogram of sugar in it. And so the probability that a single sugar machine is underfilled, you could simply calculate a p-norm problem here in R, and you'd get 1, 1.03, and 0.014. And you would end up getting a probability of 0.0162. So about a 1.5% chance that a single bag will be underfilled. Now, if we take the normal of, if we take the average of this with 22 bags. So if we were to take 22 different machines and then take the average of them, the average now is a new random variable, and we are going to assume that all of these xi are iid, and they're all with the same values as above. It will turn out that the average is also a new random variable. It's normal, so it's going to have the same expected value of 1.03, but the variance will be smaller, significantly smaller, by a factor of 1 over 22. So now, why is that important? That becomes important when you want to talk about similar calculations. So it has a reduced variance. So now we are going to take the same question that we did. So if we were to talk about underfilled, and let's say now we wanted to talk about the probability that the average would be underfilled. So in the probability that the average would be underfilled, you could think of this in terms of standardization. So I'm just going to show this to you in terms of standardization to try to drive the point home. If we were to standardize this, we would get the Z value being less than negative 10.051. The standardization would say take your X value, subtract mu, and then in this case, you'd have to divide by sigma over root n. You have a new standard deviation. The new standard deviation would be 0.014 over the square root of 22. So the chance of getting this Z score, negative 10, is effectively 0. Now, if you don't want to do it with standardization, you could just do it with a p-norm. Everything would be the same, but your variance would be, your standard deviation would be much, much smaller. And so R would spit out 0. The point of the story here, there is much less variability in the average versus the individual random variables. And so the methods that we continue on with next are going to take advantage of the fact that we have much less variability.